Okay, so for today, we'll be going through acids, bases, and oxides. So let's start. So we are now looking at page 160 of the textbook. Okay, so let's start. Okay, under acids, bases, and oxides, obviously there are the three main categories. Acids that we're going to go through first. Later on, we're going to look at bases. And the third thing we're going to look at is oxides. So there are these three main categories that we're going to look at today. Acids and bases and oxides actually belong to this whole category, which we call reactions. Okay, because when you learn about acids and bases, you are going to look a lot into their reactions itself. Okay, so let's start. Okay, so acids are actually quite common around us. Okay, acids are quite common around us. Some of the common acids that we have actually first is ethanoic acid. Okay, this is actually your vinegar. Okay, so vinegar is your ethanoic acid. This is one of them that you commonly use. The one that you commonly have in the lab is actually hydrochloric acid, nitric, and sulfuric acid. So these are the three acids that we tend to have it more commonly in the lab. Okay, now take note, first things first, hydrochloric acid formula is HCl. When you put them in water, when you put HCl in water, you actually get H plus ion and Cl minus. If you have nitric acid, the formula is HNO3. When you put it in water, you get H plus and NO3 minus. Last one, sulfuric acid is H2SO4. You put that in water, you actually get 2 H plus and 1 SO4, 2 minus. Now, what exactly are the name of these ions? So this is actually hydrogen ion. Okay, this is actually hydrogen ion. Now for this, okay, Cl minus is actually chloride ion. NO3 minus is actually nitrate ion. And last one, SO42 minus is actually sulfate ion. Okay, why I go through these names? Okay, later on you'll see me going through them a little bit more in details because salts require us to have these names. Okay, so we will further elaborate on this later on. So take note, HCl is hydrochloric acid, HNO3 is nitric acid, H2SO4 is sulfuric acid. These are the formulas you need to remember. So next part, definition. So an acid is a substance that produces hydrogen ions in aqueous solution. Now, the term aqueous solution actually just means dissolved in water. Okay, so whenever you see the word aqueous solution, it just means that the substance has been dissolved in water. Okay? Now, so for example, hydrochloric acid, when you put it in water, you get H plus and Cl minus, as what we have seen here. Sulfuric acid, when you put it in water, you actually get 2H plus and 1 SO4, 2 minus. So the hydrogen ions is what is responsible for acids. So H plus ions actually tells you that something is an acid. Okay, or you can think of it the other way around. Acid di must have the H plus ions produced. Okay, now I thought this take note is actually quite interesting per se. All acids containing hydrogen, but not all compounds that contain hydrogen are acids. Okay, so I say again, all acids contain hydrogen, but not all compounds that contain hydrogen are acids. Example that they gave is NH3 and CH4. You can see that there's H present inside these two compounds, but they are not acids. Okay, why are they not acids? Because they do not produce hydrogen ions in water. So NH3 and CH4, okay, these two are not acids. So just think note of it. Okay, now let's go on to the properties of acid now. We have talked a little bit about what are the common acids and why are they acids. It's really because they dissolve in water to give H plus ions. Now, some of the properties of acids, which I think some of you are quite familiar with. Acids have sour taste. So for example, citric acid, your oranges, your lemon, they have a sour taste because they are acidic. Okay, next, acid dissolve in water to form solutions which conduct electricity. Why are the solutions able to conduct electricity? Because in solution form, you got H plus aqueous, and you have the Cl minus aqueous, or NO3 minus aqueous, or SO4 2 minus aqueous. So when you have acids dissolved in water, they actually produce free moving ions, which can help to conduct electricity. Okay, so I say again, acids dissolve in water to form solution which conduct electricity because when they are dissolved in water, they actually have free moving ions which can help conduct electricity. Okay, next one, acids turn blue litmus paper red. I think this one, most of you are already aware of it, so I won't go through too much in detail. Now, 4, 5, and 6 is really talking about the reactions of acid. So let's look at reaction property 4 first. Acid reacts with reactive metal to form salt and hydrogen gas. So the general word equation is over here. Metal plus acid give you salt plus hydrogen. So this is just an elaboration of the word equation, more specifically to the example of magnesium. Okay, now I want to highlight this part over here. It says magnesium sulfate is a salt produced from the above reaction because I use sulfuric acid with magnesium. So magnesium is from the metal. Sulfate actually comes from the acid. So if I use sulfuric acid, I'll actually get a sulfate. So as mentioned here, sulfates are formed from sulfuric acid. If I use magnesium plus nitric acid instead of sulfuric, I will actually form nitrate because I'm using nitric acid. But if let's say I use hydrochloric acid, I will get chlorides, magnesium chloride. So depending on what acid you use, the salt name changes accordingly. So sulfuric acid will actually form sulfates. Nitric acid will actually form nitrates. Hydrochloric acid will actually form chlorides. So I just need you to take note of that. Now, this part over here talks about how can we test for the hydrogen gas that's being produced. Now, for hydrogen gas, we will use what we call a lighted splint to test for the gas. What's going to happen if really hydrogen gas is present is that the hydrogen gas, okay, let's not do this. If hydrogen gas is present, the gas will extinguish the lighted splint with a pop sound. Most students will tend to forget the word extinguish the lighted splint. So you must remember the words that are circled in green because these are the words that tend to be forgotten by students. Most will just remember pop sound. Okay, but you must take note, the gas will actually extinguish the lighted splint with a pop sound. Right? Now, I want you to take note that you realize the word here used is acids react with reactive metals. So is it possible that some metals are unreactive? The answer is yes. That's why there's this segment over here. So you mentioned that not all metals react acid to give you salt and hydrogen. So it's not all metals. So what are some of the unreactive metals? Copper and silver. They are actually the ones that do not react with your acids. Okay, now lead is a bit more complex. Okay, typically in your syllabus for NA, right, you realize that lead, they don't really test you that much because it's a bit more difficult. Right? But in case you go up to Sec 5, you may need to learn this. So lead appears not to react with hydrochloric acid and sulfuric acid. Why? It's because when you let lead react with hydrochloric acid, you actually get PbCl2, okay, plus H2. This PbCl2 is actually your lead 2 chloride. It's an insoluble salt. Same thing, if I let Pb, which is lead, plus H2SO4, which is sulfuric acid, I get PbSO4 plus H2. PbSO4 is also an insoluble salt. Now, what is so unique about this insoluble salt? So as mentioned, if you react with the two acids, you actually get either lead 2 chloride or lead 2 sulfate. This layer is insoluble in water and it coats around the metal. So I want you to look at this diagram specifically. So lead with dilute hydrochloric acid, when it reacts, it actually forms this layer around the lead itself. So when this layer of salt of lead chloride is formed around the lead itself, you realize that the acid can no longer react with the lead metal. As such, okay, when the acid cannot react with the lead metal anymore, okay, the reaction stops. Okay, so it's quite interesting that the salt actually protects the coating, which is the salt. The coating is actually the salt, protects the metal from further attack by the acid. Now, do take note, let's not use the word attack, let's use the word further reaction. Okay, so let's not use the word attack, let's use the word reaction. Okay, so in this example of acid reacting with reactive metals, so just want to summarize this a bit because quite a fair bit. Okay, we actually have the general word equation. Metal with acid will give you salt plus hydrogen. Okay. Will all metals react with acids? Answer is no. Copper and silver will not react with acid. Okay. Lead will have issues reacting with hydrochloric acid and sulfuric acid. Reason is because of the insoluble layer of salt form. Okay. So this is the first one that we went through in terms of the reactions of acids, metal plus acid. We're going to look at the next one. Acid can react with carbonates or hydrogen carbonates to form salt, water, and carbon dioxide. Now, hydrogen carbonate is very seldom tested in the syllabus. Okay, let's put an X there, but I may not put X. Let's put a wriggly line to say we put it on hold, pause it there. But acids will react with carbonate to give you water and carbon dioxide gas and the salt. So the general word equation, carbonate plus acid, give you salt, first product, water, second product, third product, carbon dioxide. So an example given is over here. This is just a very specific example of calcium carbonate with hydrochloric acid. Once again, you realize that the salt name, because I use hydrochloric acid, I get a chloride. Okay. Now, hydrogen carbonate is a little bit more cheap. Okay, this one I will say read at one time, or you can find me if you want to know further in details. But I don't want to bog down now with, on this. Okay, so this one here, read at one time. Got any questions, can look for me. But in general, you just need to know about carbonate plus acid instead of the hydrogen carbonate plus acid one. Okay, now the interesting thing is this. We know that carbon dioxide gas is produced. Okay, carbon dioxide gas is produced. So in the previous example, we learned how to test for hydrogen gas. In this segment here, we're going to learn how to test for carbon dioxide gas. So how to test? We actually bubble the gas through lime water. Okay, by bubbling the gas through lime water, we're actually testing for carbon dioxide. So this is a test for carbon dioxide. Now, if really carbon dioxide gas is present, you actually form a white precipitate with lime water. This is the result of the test. Okay, so test for carbon dioxide is actually achieved by bubbling the gas through lime water. Okay, how do I know that really carbon dioxide gas is produced? It's really when it forms a white precipitate with lime water. So many of you might ask, what is white precipitate? So precipitate is actually the insoluble solid particles produced in a liquid by chemical reaction. So it refers to the solid particles, okay, that cannot be dissolved in water. Okay, so I say again, the precipitate actually are just insoluble solid particles. So just take note, precipitate are insoluble solid particles. Okay, so carbonate plus acid give you salt, water, and carbon dioxide. Last one, okay, number 6. Acids react with metal oxides and hydroxides to form salt and water only. Now, acids react with metal oxides and hydroxides. This one, I'll generally categorize them as bases. Okay, so acids react with metal oxides and hydroxides to form salt and water only. So first one, Metal oxide plus acid gives you salt and water. Metal hydroxide plus acid gives you salt and water also. So whether is it the oxide or whether is it the hydroxide, you will always get the salt and the water. Okay, so number one is actually this whole part here. Number two is actually this whole part over here. Okay, so acids react with your bases to form salt and water. So just in summary, okay, before we go on to the next part, really in terms of the reaction here, I'm going to just summarize what the three you must know. Acid can react with metal. Two, acid can react with carbonate. Three, acid can react with bases. The bases we are looking at is either your metal oxides or metal hydroxides. Okay, so this is actually the three reactions that we've gone through more in details. So take note of them because it's commonly tested. Okay, now, next one. What is the role of water in acids? So I just need you to just take note of this, is that acids only display their properties when they are dissolved in water. Okay, so if there's no solution, there's no water, right? Okay, there will be no H plus ions, which then the acid cannot behave like an acid. So just, what do I mean by that? Example, HCl typically exists as a gas. So hydrogen chloride is normally a gas. Okay, but when you dissolve it in water, it becomes HCl aqueous. Now, this guy here, HCl gas, doesn't display any properties of acid. But once you have dissolved it in water, you get HCl aqueous. This fella here now behaves like an acid. Why is it so? It's really because when you dissolve it in water, you're going to get the H plus aqueous ions. Okay, so water is really required, okay, in order for your acid to work. Okay, that's why you always realize that it's always HCl aqueous, HNO3 aqueous, H2SO4 aqueous. These three are your common acids, and you realize that it's always AQ, 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 which means that they are dissolved in water. Okay, so just take note of that. Right, you can read further in details over here in terms of why HCl needs to dissolve in water. Okay, generally more for the combined and the pure students. Okay, combined science express and for the pure students. For NA side, just need to know this basic fact over here. Okay. Next part we're gonna go through, okay, is actually on the basis. But in general, as a summary for acids, we went through that acid is a substance that produces hydrogen ions in aqueous solution. This one is sort of like a definition for acid. Then we went through the 6 different reactions. Okay, that was what we went through just now. Now we're going to go on to bases and alkalis. Okay, we're going to go on next to bases and alkalis. So at this particular point, okay, take your mind off from acids for a while. We're going to go on to bases and alkalis. So what are bases? So a base is any metal or hydroxide that reacts with an acid. So bases are any metals, oxide or hydroxide that react with acid to give you salt and water only. Okay, now you understand why I did mention just now that when they say acid plus metal oxide, metal hydroxide, I did mention the word base. It's really because that metal oxide, metal hydroxide can react with acid, right? So we can classify them as bases. Okay, so what are some of the common bases that we have? Sodium oxide, zinc oxide, copper 2 oxide, magnesium hydroxide, aluminum hydroxide. These are all some of the common bases. Okay, common bases. Now, but in general, okay, there are more than this. Okay, now, so what's the reaction for bases? So as mentioned, base can react acid to give salt plus water. So there are two main products here, salt and water itself. Okay, do take note, most bases are insoluble in water. Okay, most bases are insoluble in water. So all the examples here, given here, all the common bases from the sodium oxide all the way to aluminum hydroxide. Actually, these four at the bottom are insoluble. Only this guy here is soluble. Okay, so actually most bases are insoluble as mentioned over here. So the question is, okay, most bases are insoluble, then the soluble ones, are they special? Sort of, I would say, sort of. So in this next part here, we're going to elaborate more on those bases that are soluble in water. So bases that are soluble in water, we actually give them a special name called the alkalis. Okay, alkali is a name that definitely you are more familiar with. So an example of a soluble base is actually sodium oxide, as I mentioned above. When you put sodium oxide in water, you actually get sodium hydroxide. So this is one of the alkalis that you commonly use, okay, in the syllabus. So common alkalis, what I have, sodium hydroxide, potassium hydroxide, calcium hydroxide. Now, barium hydroxide, you will seldom see it, so I'll just put an X over here. Now, there's another alkali which is not so that you commonly see that's not listed here. Okay, this one you might want to write it down in your textbook. It's actually ammonium hydroxide. Okay, why they don't really put it inside here is because it is not a metal oxide or metal hydroxide. Okay, the formula for ammonium hydroxide is actually NH4OH. When you put in water, you actually get NH4 plus equals, you get OH minus equals. So ammonium hydroxide got this, okay? Now, there is another name given to ammonium hydroxide. So the other name that you'll see it quite often is actually called aqueous ammonia. So some people say, how is aqueous ammonia the same as ammonium hydroxide? So ammonia's formula is actually NH3. Ammonia's formula is actually NH3. Now, it behaves like a gas. Sorry, no, it doesn't behave. It is a gas. Ammonia is actually a gas. When you dissolve it in water, it's sort of like add water to it. And when you mix these two together, you dissolve the gas in water, you actually get ammonium hydroxide, okay, which we term this as aqueous ammonia. So do take note that aqueous ammonia is very commonly used, very commonly seen. It's actually one of your common alkalis. So what exactly are alkalis? An alkali is a substance that produces hydroxide ions in aqueous solutions. So I will say again, alkalis are substances that produce hydroxide ion in aqueous solution. So once again, whenever we see the word aqueous solution, remember the idea of dissolved in water. Okay. Now, so examples are as follows. So for example, sodium hydroxide, when you put it in water, you get Na plus and OH minus. Calcium hydroxide, which is also your lime water. Okay, so calcium hydroxide is actually your lime water. When you put it in water, and when you dissolve it, it actually splits into Ca2 plus and to OH minus. As mentioned here, ammonia gas dissolves in water, ammonium ions and hydroxide ions are formed. Okay, so I put it up here. Ding, ding. Anyways, like this later, you're all confused. Okay, so this is the one which I've drawn just now, we have written just now. Now, so we learned about these common alkalis that we have here. So we know that alkalis are substances that produce hydroxide ions when dissolved in water. So we've gone through some basic idea of what alkalis are. Now let's think in terms of how do they react. So first thing, alkalis have bitter taste and feel soapy. So one of the common examples I like to give my students is actually the yellow noodles, the thick yellow noodles that you all use for mirubus. Okay, example of the mirubus noodle. Miribus, mirubusa. Now, the mirror noodle that you see, the yellow noodle, if you ever got a chance to take it up, okay, without the gravy, when you feel it, okay, it actually has this very soapy feel. Okay, and if you just eat it like this, it's actually quite bitter. So one of the idea is that if you want to overcome the bitter taste, you actually add lime to it. Lime actually is an acid, okay, not lime water. Take note, lime and lime water are different things. You actually like lime, you add lime to it, you actually will neutralize the alkali. So it's quite interesting in that sense. Next, alkalis can actually turn red litmus paper to blue. Okay, opposite from the acids. Acids are blue to red, but alkali is red to blue. Next, alkalis react acid to form salt and water only. Now, this is the start of the reaction already. So alkalis react acid to form salt and water. Do you realize that this reaction looks very familiar? Why? Because we learned in the previous one is that acid plus bases gives me salt and water. And we know alkalis are a special group or a special class of bases. So in actual fact, this reaction over here is similar to this. Okay, this reaction over here is similar to this. Okay, so now at this particular point, this term is introduced now. Okay, when we have H plus ions, which is from the acid, when we have hydroxide ion, which is from the alkali, okay, we actually undergo this reaction called the neutralization reaction. Okay, so the neutralization reaction is actually when the H plus and the OH minus come together. So you actually will have this ionic equation over here. Now this one, I'm going to put a star here because this is the only ionic equation that keeps coming out. So you must know that whenever you see the idea of neutralization, well, it's really the idea of acid reacting with alkali. To be more precise, it's actually the H plus reacting with the OH minus. Hence, the equation that should come to your mind is actually H plus aqueous plus OH minus aqueous to give you H2O. Okay, so this reaction, you must take note of it. It's quite an important reaction. Okay, so this is just further elaboration on the reaction itself. I won't go into details, but you can read up on your own. And most of you should be quite familiar with this already. The next reaction that alkalis will actually undergo is that alkali plus ammonium salt will give ammonia gas plus salt. Plus salt plus water. So the general equation is listed here. Alkali plus ammonium salt will give you three products: salt, water, plus ammonia gas. Right? So they got an example here. So calcium hydroxide, which is an alkali, when it reacts with ammonium chloride, this is an ammonium salt. It's going to give you a salt, so calcium chloride, water plus ammonia gas. So at this particular point, most students will actually ask, Cher, ammonium salt. What are ammonium salts? So do take note, there are only three main ammonium salts in your syllabus. First, okay, it's actually ammonium chloride, okay, which is in this example over here. The second one is actually ammonium nitrate. Third one is actually ammonium sulfate. So these are the three ammonium salts that you will see, and hence do get familiar with them. For those of you who are quite sharp, you realize that ammonium chloride, ammonium nitrate, ammonium sulfate, chloride, nitrate, sulfates are actually similar to the salts they can get from using hydrochloric acid, nitric acid, and sulfuric acid. Okay, so chloride, nitrate, sulfates are your three common salts that you need to be familiar with. Okay, next. Now, as mentioned, this is the reaction. So we learn how to test for hydrogen. We learn how to test for carbon dioxide in the acid reaction. Now we have another gas that's coming out, which is called ammonia. So how do we test for ammonia? Do take note, ammonia can be recognized by its characteristic pungent smell. So there's this very unique smell about it. So I told many students before, if you want to remember how the smell is like, okay, you can go and exercise, have a very sweaty shirt, put it in plastic bag and seal it up. Okay, when you open it, maybe 1-2 hours later, you realize there's this very special smell that comes out of it. That's actually the ammonia gas. Right now, so how do we test for ammonia gas? We actually use a moist red litmus paper. The word moist is important. Please take note, you need to use the word moist whenever you're testing for ammonia gas. What will the ammonia gas do? If this is the test, the result to know whether ammonia is present is that the gas must turn the moist red litmus paper to blue. Okay, I say again, the gas must turn the moist red litmus paper to blue. What's actually happening here? Okay, it's actually quite interesting because the ammonia gas actually dissolves in the moisture, which is actually water, and it's going to give you NH4OH aqueous. And this guy here is actually your alkali. And that's why your red litmus paper will turn blue. Okay? So this is the reaction for ammonia gas. Okay, no, sorry, this is the reaction for alkali. And this is the part where we're going to test for the ammonia gas. Okay? So what have we gone through here? We learned that a base is any metal oxides or hydroxides that will react acid, use salt and water. So that's the idea of what a base is. Any metal oxides or metal hydroxides that react acids, use salt and water. Next, an alkali is a substance which produces hydroxide ions in aqueous solution. They are a very special group of base because they are able to dissolve in water. Then we went through 4 reactions for alkalis. Okay, 4 main properties, sorry. First property is here, have bitter taste and feel soapy. Second one, turn red litmus paper blue. Second one, third one is react acid to form salt and water. Fourth one is it produce ammonia gas when heated with ammonium salt. And the last one we did mention from reaction 3 is actually about neutralization. So in summary, in terms of the reaction of acids and alkalis, okay, if we don't count the bitter, acidic, bitter, sour taste, all kind of stuff, we just focus on what the acids and alkalis react with. You can actually summarize them into 4 main reactions. So the first one is acid plus metal. It will give you salt plus water. Salt plus hydrogen gas. The second one, acid, can actually react carbonate. What will it give you? It will give you salt plus carbon dioxide plus water. Third reaction, acid can react with your base or your alkalis, because bases are a special group of alkalis. Alkalis are a special group of bases. We give you salt plus water. And the last reaction here is actually alkali plus ammonium salt. It will give you salt plus water plus ammonia gas. So these are the 4 reactions that I need you all to just take note of and remember, because a lot of your questions, they like to test on these reactions. Okay, so out of all the reactions that we talked about, it can just be brought down to actually these main 4 to remember. Okay? Next part here is the pH scale. So I think many of you are familiar with it, so I will not go through too much in details. But do take note, pH ranges from 7 to 14. Acids have pH less than 7, alkalis have pH greater than 7, and neutral is exactly 7. So what does it mean? It means that when I have pH 0, 7, and 14, 7 is exactly neutral. Anything more than 7, we consider them as alkali. Anything less than 7, we consider them as acid. only when the pH is exactly 7, then it's considered neutral. Okay? So the pH of a solution is actually related to the concentration of hydrogen ions and hydroxide ions present in solution. Just need to know that. Okay, that's all you need to know. Okay, a lot of this further explanation is really for you to understand better lah. Okay, now, but this part here, I want you to take note. Okay, this color scheme here that you see, 7 being neutral, is actually green. 14, 12 to 14 is actually quite alkali, strong alkali. The color actually is about blue to violet. Whereas 0 to about 2 is about red color. Okay, it is about strong acid. So it is really about red color. Now, so why do I want to pause here talking about the colors? Because this color scheme here actually is a very good reflection of what colors the acids or what color solution will actually produce when they are put in universal indicator. So universal indicator is like a substance that you add in to find out what pH it is based on the color that you can observe. Again, based on the color you can observe, you actually determine whether is it going to be acidic, neutral, or alkaline. Okay, so universal indicator is one of the ways you can use to test what the pH is. So, okay, if you want to test for pH, we'll use this compound called the indicator. You can also use pH meter or pH sensor attached to a data logger. This tool is a bit more high-tech, more high-tech. But in the lab, we typically use the indicators. Okay, we do have data loggers in the lab. We can use them. Okay, but generally, when you are doing experiments, we will use an indicator to determine the pH value. So as mentioned just now about universal indicator. So universal indicator is actually a mixture of dyes. Okay, it gives different colors in solutions of different pH. So this is the chart that you will typically have if you are using a universal indicator in the lab. However, for NA side, you don't really use the universal indicator that much. You don't really have the chance to go to the lab that much also. So in a scenario here, for universal indicator, I just need you to take note that acidic, we will typically see red. Neutral, we will typically see green. And alkaline, or alkaline, we'll typically see blue or violet. So remember this color scheme. Okay, this is the color scheme for universal indicator that you need to take note of. Okay, all the different other indicators that you see here, okay, the only one that really matters to you is litmus. The rest of it don't really come out that often. Okay, but you need to know that this methyl orange, screen methyl orange, bromo-thymol blue, phenolphthalein, all these are the other indicators that is actually that you can use to sort of like to test in terms of the pH value, whether is it acidic or alkaline. Okay, so what's the importance of pH level? You know, okay, so this is just an application of it. Do take note, blood is slightly alkaline, pH value 7.4. Okay, now when you're given injection, just like your vaccine that you're having, generally they'll make sure that the vaccine that you receive have a pH of about 7.4. Okay, now if the pH changes by about 1, so 7.4, if I change it up to 8.3 or change it down to about 6 point something, the person will die. Okay, so our blood is really maintaining about pH 7.4. So slightly alkaline, but it's quite near neutral. Okay, if it goes higher or goes lower, it's going to cause us to die because our system in the body wouldn't function. Okay, so it's quite interesting there. Next thing, Why is the pH of soil important? You realize in the test papers or the prelim papers that I received so far, they like to test on the pH of soil. Okay, soil. So take note, pH of soil can vary from 4 to 8. Okay, that means it can be acidic, it can be alkaline. It really depends on the type of soil. Okay, now, so that's why it's important. Different plants grow in different pH, soil pH. So we need to make sure that we can adjust to the best for them. Okay, so do take note, most plants will not grow if the pH of the soil is below 5 or above 9. And why it can be unsuitable, sometimes because you add too much fertilizers, or sometimes it can be caused by the acid rain. So what should we do to adjust the pH of the soil? So do take note, you can actually control the acidity of the soil, okay, by adding quicklime or slick lime. Now, these two are quicklime, slick lime, they are actually your bases. Why? You realize metal oxide, metal hydroxide. So you can only add these two in if your soil is too acidic. If your soil is too acidic, the pH is low, you can add bases in to raise the pH. Okay, so actually by adding quicklime and slick lime, which are the bases, we actually help to increase the pH of the soil. Okay. Now, but take note, we won't add too much, because add too much, it will raise the pH too much. So adding too much base will make the soil too alkaline, and hence the plant become unsuitable again. So it's important to add the right amount. Okay, I say again, it's important to add the right amount, not too much, not too little. Okay, so what we have gone through just now was a lot more on the pH side. Acid with a pH less than 7, alkaline pH more than 7, and neutral is exactly 7. Next, when we talk about pH value, okay, the higher the concentration of H plus, the more acidic the solution is. The higher the concentration of OH minus, the more alkaline the solution is. Okay. Next, plant grows well when the pH is around 7. How can we help to control it? We can actually add quicklime, which is calcium oxide, or slick lime, which is calcium hydroxide, to reduce the acidity of the soil. So these were the 4 points that we have gone through just now regarding pH. Right? So this one, you see quite a fair bit in the MCQ question. This one, you need to take note, especially about the colors. Okay, especially about colors. Okay? So this is the third part. And now we're going to go on to the final, last part, which is on the type of oxides. So let's start off with really what are the 4 main types of oxides. First, you got acidic oxide. Next, you have basic. Third, you have amphoteric. And fourth, you have neutral oxides. So what exactly are oxides? So an oxide in simple terms is actually, okay, a compound of oxygen and another element. So it's a compound formed by an element together with oxygen. Okay, that's why they are called oxides, because it includes oxygen. So there are 4 main types: acidic, basic, amphoteric, and neutral. So most oxides of non-metals, are acidic. Okay, why are they termed as acidic oxides? Okay, it's because when they dissolve in water, they form acids. So some of the common ones that we see here in terms of acidic oxides are as follows. Carbon dioxide is an acidic oxide. It normally is a gas, but when you're dissolving in water, you actually get carbonic acid. Sulfur trioxide is a non-metal oxide. Dissolving in water, you get sulfuric acid. Phosphorus 5 oxide, P4O10, is a solid. You dissolve in water, you get phosphoric acid. This can be found in Coke, okay, or Coca-Cola that you eat. Okay, now, so obviously because they are acidic oxides, they will react with alkalis to form salt and water. However, do take note, they do not react with acids. So take note, first thing, acidic oxides do not react with acids, but they will react with alkalis to form salt and water. Okay, so you realize that the reaction looks a bit chima. So typically when we do test you on oxides, okay, on their reactions, we will seldom ask you in terms of writing the chemical equation. But we just need you to know whether the acidic oxides or the other type of oxides, whatever oxides it is, do they react acids, do they react alkalis? Okay, that's the two things that they'll keep asking. So I say again, the two things they'll keep asking is, does the oxide react with acid? Second thing, does the oxide react with alkali? Okay, so you realize this two thing will keep coming out. Now, so the question that we can go on to talk about is, okay, these three I understand. Now, silicon dioxide is sand. You put sand in water, it doesn't dissolve at all. So can we ask ourselves, would silicon dioxide be classified as an acidic oxide? Okay, so it doesn't react with water, but it does react with concentrated sodium hydroxide to form sodium silicate. So because silicon dioxide reacts with alkali, it doesn't react with acid, and silicon dioxide is an acidic oxide. So we will always use these two questions to think in terms of the classification. So acidic oxides react with alkali, they react alkali, but will not react with acids. Okay. Now, next one, basic oxides. So next part, they say most oxides of metals are basic oxides. So they're insoluble in water, but there are some that will, which is sodium oxide and potassium oxides. Now, so the question is, how do we know whether something is a basic oxide? Basic oxides will react with acid to form salt and water. Okay, so basic oxides will actually react with acids to form salt and water. So this one, thick react with acid. Now, what is not mentioned here is that actually they cannot react with alkalis. Okay, so basic oxides can react with acid but cannot react with alkali. Now, going back up here, if you want to do the same kind of writing, acidic oxide is thick. It's cross first, cannot cross in terms of its reaction, so cannot react with acid. Thick can react with alkali. Okay, so that's based on all the descriptions we have gotten so far. Now, acidic oxides are the most common type of non-metal oxides. Basic oxides are the more common types of metal oxides. Then you realize, okay, you have talked about two of the oxides. How about the other two? So the next one that we're going to look at is amphoteric oxides. So this one is interesting because they are metallic oxides. So take note, they must be metal, reacting with both acids and bases. So this one here is thick, react acid. This one is also thick, react with alkalis. So this is actually how you differentiate between whether it's acidic, basic, or amphoteric. So amphoteric oxides are actually metallic oxides. So they must be metal oxides that react with both acids and bases to form salt and water. So this reaction here, don't need to remember, but do take note, there are three main amphoteric oxides you must remember. Okay, aluminum oxide, lead oxide, and zinc oxide. Now, some students ask, how to remember? Okay, if you look at the formula here, if you put zinc on top, you actually form a ZAP. So amphoteric oxide, you can think of Z, zinc oxide, aluminum oxide, or lead-2 oxide. That's if you think in terms of the formula. If you think in terms of this, okay, they are just the name itself. Okay, students, I can tell them, you can think in terms of LACE. LACE is for lead, aluminum, and zinc. So whichever is easier for you, remember it that way. Okay. The last one we're going to look at is neutral oxides. So non-metal oxides, can actually form oxides that shows neither basic nor acidic properties. What do they mean by this? It means that if they do not have basic properties, means that they will not react with alkali. Sorry. Basic properties means that they will not react with acids. Okay. Acidic properties means that they do not react with alkalis. Okay. So these are the neutral oxides. So neutral oxides, they don't react with both acid and alkalis. So some examples in your syllabus, remember, is water, carbon monoxide, and nitric oxide. 1, 2, 3. Now, how to remember this? I tell my students, remember as no cold water. No cold water. Okay? So that's one simple way of remembering what are the 3 neutral oxides. So how do we classify them? Okay, I mean, after going all through all this, what if I got an unknown oxide? Okay, they say like, for example, XO. Okay, or element X react with oxygen. Okay, so you form an oxide, right? So how do I know whether it's going to be basic, acidic, or amphoteric, or neutral? So really the key question to ask is, does it react with acid? If yes, it will definitely be basic or amphoteric. If no, it will either be acidic or neutral. Then of course the next question to ask is, does it react with alkali? If it reacts with both acid and alkali, it's amphoteric. If it reacts with acid but doesn't react with alkali, it's basic. So I say again, if it reacts with acid and then it reacts with alkali, it is amphoteric. Then I'll use green now. If it reacts with acid but it doesn't react with alkali, you got basic oxide. The next one we're going to look at, if it doesn't react with acid, but it reacts with alkali, that is an acidic oxide. And the last one, I'll use pink. It doesn't react with acid, it doesn't react with alkali, we actually get the neutral oxides. So that's how you go about classifying this 4. Okay, now, if let's say the question never really explained to you whether it can react acid or alkali, what is another way you can go about understanding whether it's acidic, neutral, basic, or amphoteric? So I want you to draw this table out, okay, you can copy it down in your book, okay, which is this. So you can actually ask yourself, in terms of the oxide, right? Ask yourself, is it a metal or non-metal? So if it is a metal oxide, if it's metal, then it is a metal oxide. If non-metal, it's a non-metal oxide, right? Now, take note, for metal oxides, there's only 2 possibilities only, amphoteric or basic. Non-metal, there's 2 possibilities also, acidic or neutral. So because there's still 2 possibilities, we're going to ask ourselves the next question. Okay? Amphoteric, because in your syllabus, you only learn 3 examples, right? So to know whether it's amphoteric or not, you ask yourself, is it zinc oxide? Is it aluminium oxide? Or is it lead oxide? Only these 3 are amphoteric. If the metal oxide is not any of these 3, that means it must be basic oxide. Okay, so I say again, because amphoteric in the syllabus is only these 3, zinc, aluminium, and lead. So anything that's not zinc, aluminium, and lead, you realize that, oh, they must be basic oxides. Okay, so you go by elimination. Same way we're going to do is for non-metal. So in your syllabus, you actually learn that there's this thing called the neutral oxides. Now, what are the 3 neutral oxides in your syllabus? I mentioned is no, coal, water. Okay, so all non-metal oxides other than these 3 are actually classified as your acidic oxides. So how you go about differentiating is actually knowing the amphoteric, then you can determine basic. Knowing the neutral, then you can determine the acidic. Right? This one will actually require some practice. So let's look at some examples that I have here. So let's think through. Example, I got magnesium oxide, MgO. So magnesium oxide is actually a metal oxide. So I know under oxide, it will go under metal. Metal oxides over here. Then the next question asks is it zinc, aluminum, or lead? Because it's not any one of these three, magnesium must be a basic oxide. Next one we're going to look at, I'm going to give a non-metal example. Could be nitrogen dioxide, NO2. So nitrogen dioxide, nitrogen is a non-metal, so I know it's a non-metal oxide. Then I ask myself, NO2, nitrogen dioxide, is it the neutral oxide? NO is nitrogen monoxide. So it's not this, not this, not this. Therefore, nitrogen dioxide must belong to acidic oxide. Okay, so that's one of the ways you can go about thinking through. Okay, so that will be it in terms of the syllabus for acid, bases, and oxides. So this MAPIT is actually a very good branching out to show you what is this whole chapter about, what are the things you need to remember. Okay, so I say again, this MAPIT is actually a very good summary. So if you ever need to do a quick revision, this MAPIT segment is actually quite good for you. Okay, so that's all for today. I'm going to stop the recording now.